Because you're really good at process server.
Yeah, so that's like, so that's fine.
Yeah, I had JavaScript. I wrote the JavaScript. It's kind of cool because it like fills in huge sections for me, and I don't have to get chunks everywhere.
Yeah, and so it's having stuff automated, like if you don't have to do as much.
Have you ever implemented transclusion before? Or, so let's say you have like a project proposal and you want to pull a section from the project proposal and put it in the process.
Yeah.
So you just tell JavaScript, go touch the other one, yank out the piece and then attach it to your DOS.
Load it into.
So I can just explode all the processes that have the card,
Like
reassemble it.
I know. She said she would have.
And then you don't have to do it. If you make one change, it goes propagates everywhere else.
That's pretty cool. So then it goes, like you're literally pulling pieces of it into like a separate JavaScript file.
And then media orders. It's just when it's good on the screen, CSS style. Like for print, you want to remove the screen only little warnings. So when it's print, it adds page breaks where there needs to be page breaks, and it removes a bunch of labels to tell you where it came from. So yeah, those are called media orders.
I used it for I'm just not saying like it's not No, I don't want to see it.
You know what Chrome uses Firefox instead of Chrome?
I could ask you. It's probably a So I think when I was watching the way that content looks like Firefox.
Because I'm thinking both Firefox and Chrome, and I found that there's always connectivity. Super careful about.
I mean, I use Chrome when you specify which browser it works on or which one it's
I'm having a hard time with Edge and Internet Explorer. Those two are broken.
Yeah, I would use that.
And Safari doesn't support half of it. All of the stuff like web app and DP9 and all this stuff.
Your best bet running.
There's no way.
Something with
One version. I don't know.
Oh yeah.
So just push it. So I don't know what really
Okay, welcome back everyone. Today we'll be wrapping up networks by just like talking about trees. We haven't really talked about trees at all. And then we'll go into what are like typical visualization tasks and how do we design visualizations, and then if we still have time, I'll talk a little bit about evaluation, but honestly I think we'll probably talk about evaluation on Thursday. So just to recap, when we talked about network visualization, we had like the network visualization for topological structures, and then we had Carolina's guest lecture on multivariate networks. But just to recall, like what are the major types of network visualizations? There are these explicit visualizations, the node link diagrams that we all use, matrices, adjacency matrices, and implicit visualizations. And implicit are like only suitable for trees, and so we'll talk about those today. Just recall, like for node link diagrams, this is kind of like we have three styles. We have the free form layout, where we really can kind of like optimize the layout so that we can see the topology of the network. We have a style layout, which is useful in some contexts when you have like some structure given, for example, the sequence of the DNA, and then you have fixed layouts where you have like all the positions of the nodes given exactly. These are useful if you, for example, want to visualize something on top of a map. And we talked about that we have criteria for node link layouts, like such as trying to minimize edge crossing, uniform edge length, and so on, but those are usually conflicting. And we can try to like optimize a layout by using, for example, a standard optimization approach according to those algorithms. But in practice, what people use a lot are these physics simulations that kind of get a little bit of some of those objectives, like force-directed layouts, where we have this spring-embedded physics model that we can run. Then we did talk a little bit about adjacency matrices, and so adjacency matrices really, like instead of using like these nodes and links here, where, as you can see it on the left, we have like a matrix where each row and each column corresponds to a node, and the filled-in cells correspond to the edges. And so here you have an example of a symmetric matrix because this is an undirected graph, so you have like basically the same edge entries on both sides of the diagonal. And as with all kinds of tabular representation, it's really important to get the ordering right in adjacency matrices. And so you often need to use some pretty fancy algorithm to do that. There is, for example, the library reorder.js that gives you lots of different approaches to reorder them. So now I want to jump into trees, and here specifically into an exercise. This is kind of like a multivariate tree exercise. I would like you to kind of like, this is kind of like my data, my folder hierarchy that I have from the visualization class in 2017. So you see, and this is a subset of it, you have DataVis 2017, then you have the lectures, you see a Keynote file, then you have a subfolder, then you have some more Keynote file, then you have your exams and your exercises. And I would like you to draw in teams two different visualizations that show both the directory structure and the size of the directory and the contained files. So I have the instructions here, and I'll give you guys 10 minutes and like, go ahead and work with other people, and then we'll look at some of your solutions.
double.
Figure out.
We're on the all well, the other one,
So say like so it's divided into chunks. Like if you're this folder.
Okay, everyone. So, what were the kinds of designs that you came up with? Tree map. So, what, like, how did you code your tree map?
So the size of the squares is the size of the files and the directories.
Yeah, and the directory size is the sum of the files it contains. Exactly. And this is also what I've sketched here. Not very beautifully done, but we'll talk more about tree maps later.
You want these to be like proportional by area, right?
Yes. And yeah, rough guesses, right, for a sketch. Like, it's kind of tricky to do this by hand, of course, because you need to sum up all of the files and then like do this proportional by area. But unfortunately, you have to tilt your head if you want to look at this. But like what I did here is like draw essentially a tree map, and the red ones here, the red outline here are the folders, and the green outlines here are the files. And I did label each of the files. Like, what's an obvious problem with a technique like this?
You have really small files.
Exactly. So you can't label it with the small files.
If you have a lot of different entities, it's impossible to scan and search for a specific one.
Yeah, so you can't really recognize every entity. So this assumes really that the size that you're using is really the most important attribute. Anybody drew like a node link diagram for the trees? Yeah. And how did you encode the attributes?
Just kind of having layers and just having the size written on the node.
Okay, so like just a labeled representation. Okay, so as you can see, like there's many different solutions to visualizing trees and their attributes, and so we'll be looking at some of those today. And but the classical thing, of course, is explicit tree visualization, right? So this is like, well, you could do a force-directed layout, but in trees it's actually easier than that. You don't need, like, you actually have a couple of different rules. You usually want them to be directed from some root. And so here are two different layouts. We have both are angled tilted layouts. One starting here from the left and progressing to the right. One here is a radial layout. And so you see the root and then all of the children, and then it's children's children and so on. And so you can imagine writing an algorithm like this where you probably go through, like you would write a recursive algorithm that goes through the root, the leaf nodes, and then calculates for each of the nodes, inner nodes, how many leaves do you have, or do your children have in total to calculate that layout. You can then you can make those interactive because trees are usually, like since they're hierarchical, you can easily take this super node approach. So you can collapse. Well, this one can't collapse it, okay. But there's D3 implementation out there that can actually collapse the nodes. I probably had a link on the other one. And so if you compare those two here, what are the pros and cons of the linear and the radial layout?
No, I'm saying.
It's easier to read the labels on the linear layout than on the radial layout.
Exactly. So easier to read the labels. Text readability is always a concern. What's the benefit of the radial layout?
Space maximization.
It maximizes space, yes. Because if we have trees, we tend to get very long trees, and you can notice that this tree is actually cut off, whereas it fits easily into our regular screen space if we do this radial layout. And like I've showed you this video, the mother of all demos, where they demonstrated the use of the first computer mouse. But they actually also introduced interactive tree manipulation here. So they had drill downs and roll ups for trees, and also unbalanced drill downs. And what's an application where you might be using this every day?
File Explorer.
File Explorers, exactly. So if you use a File Explorer that supports hierarchical trees, then you can selectively unroll any of those leaves. So that's a very basic idea that we can that we use every day. So here's this interactive example now. Here is this tree. I can dynamically expand it, right? So because it's kind of because we have this hierarchy, we have a natural way of grouping things. So here, this is the Flare package hierarchy. So we see that we have data, we have Flare, data, and we have converters. And all of this makes sense because they're structured hierarchically. So we have this nice level or this nice way of aggregating them naturally. And then here is a video, one big area of trees, and actually a project that Jen is working on right now is phylogeny, right? If you want to understand how evolution works, you need to study the tree of life. And one thing that's unfortunately true is that trees of life are not we don't have ground truth for them, right? So they are always constantly evolving. We can now use genetics to kind of uncover familial relationships between species. But in the end, as the further you go back in time, the less certain your trees are. And so what you have is these massive sets of alternative trees, and this is what this particular paper here tried to tackle. I'm gonna just play this video briefly. This is a little bit older, a classic paper, and one of the few visualization InfoVis papers that was published
Biologists are often faced with the task of comparing many similar phylogenies, that is, trees that describe evolutionary relationships between species or genes. Although some sophisticated tools for tree manipulation exist, for instance Maclade as shown here, they are designed for small data sets of dozens or hundreds of nodes, and they have very limited support for comparison between trees. The spread of DNA sequencing is leading biologists toward the creation of much larger trees, thousands of species today, and millions within the coming few years. We present Tree Juxtaposer, a new tree visualization tool supporting scalable comparison and navigation of phylogenetic trees of over 300,000 nodes. Even small trees are hard to compare with visual attention alone. Late highlighting of nodes and subtrees helps. Perfect matches for named leaves are easy to find, but computing the best corresponding nodes in the interior required a new algorithm that runs in n-log-n times slow. Highlighting alone can still lead to false negative conclusions. We see two leaves highlighted in exactly the same spot on both sides, but their structural relationship to the rest of the tree differs. We can mark the exact place in the tree where structural differences occurred using the results of the corresponding node computation. Subtrees underneath the black edges are guaranteed to be contiguous on both sides. The red edges show where a subtree from one side maps to a non-contiguous area in the other. Mouse over highlighting also allows us to check this property on the fly. Biologists call continuous subtrees a clade, and determining whether a clade in one tree is also a clade in the other is a recurring core question. When comparing these larger trees with 4,000 nodes, automatic detection and marking of structural difference is even more critical. Our new navigation technique, where growing one area leads to shrinking of all other places that don't share the rectangle.
So this is a classic zoom focus and context technique, right? So yeah, I don't want to go too much more into more detail here, but essentially, like even something as simple as tree visualization, there's still a lot of unsolved problems, especially if you get into comparison. And as you can imagine, like I haven't really talked about it, but graph comparison, graph evolution, and so on are still like pretty complex and open research problems. So now I want to move on to implicit layouts for trees. And so we talked a little bit about tree maps today, but tree maps are only one class of implicit layouts. And so there's these three types, the tree map, sunburst, and icicle plots, and they're actually, like, at least those two are fairly similar. But what is the idea of implicit layouts in general? The idea is that we don't actually explicitly visualize edges. So none of these visualization technique here shows an edge. And we see the tree structure really just by smartly arranging stuff. So we use positional encoding to visualize the trees. And so in the case of the tree map, it's nesting. In the case of sunburst and icicle plot, it's adjacency. And we'll talk about them one by one. So tree maps are like the classic example of this. This is like a seminal paper from Johnson and Snyderman in 1991 that they essentially came up with the idea, well, why don't I visualize a tree by hierarchically nesting boxes, and why don't I visualize some attributes by simply assigning a box a certain height? And so, like, I think by now you probably already understand how a tree map works, but here's kind of like an illustration. So the white circle here is the root, and the root is actually not explicitly shown, right? This is the big rectangle outside. And then we have 4 leaves or 4 nodes at the second level, 2 of them leaves. And so we can easily spot the green and the yellow leaf. And notice that here we actually don't have any attributes. We simply encode each. We simply encode them to be equally sized at each level. Then for the blue one, we have 4 subnodes, 3 of them leaves that you can see here. And then the gray ones here at the very bottom are up here. And then for the red one, you can see this correspondingly here. And so, like, what's an obvious weakness of this technique?
To be divisible.
What's that?
You need it to be divisible by 2 to get that nice.
Yes, but usually you can get that to work. not as like nicely geometrically, right? But you can like change. You can adjust the shapes.
Boxes get really small.
But yeah, boxes get really small, but the biggest problem, I think, is that you don't actually see the intermediate nodes, right? So you don't see this node here, or you don't see this node here. So these tree maps, they really they focus completely on the leaves, and all of the backbone of the tree is only implicitly available. This isn't actually the case for this thing here, and I'll talk a little bit more about why that is. So one problem that if you just naively implement this, you get into this problem that you just mentioned, that our boxes get oddly shaped. And so this is like the original paper that introduced tree maps. And as you can see, these boxes, they tend to be like, they have odd shapes, right? We have these very long shapes here. They're simply not well represented. So we have these thin slices. And that's problematic. And so there's this paper by Bruce, Huitzing, and Van Wyk from 2000 that introduced the idea of squarified tree maps. So they essentially, they kind of like, you can come up with a heuristic saying that you want to, like for each square, you want the aspect ratio of the sides, or for each rectangle, you want the aspect ratio of the sides roughly equal. So like you want to essentially get squares if you can. And so they proposed this algorithm here. And so the idea is that you simply keep adding elements iteratively until you start kind of like making your aspect ratio worse. So like in step 1 here, they add, like we have this tree that has these elements 6, 6, 4, 3, 2, 2 to 1, and we try to make a squarified tree map out of this. And so they start by taking the largest piece, the largest leaf, and adding it here. And so this is what you see. And they chose to split it here horizontally because if they added this vertically, the aspect ratio would be worse. So this is how they make the decision to split it horizontally first. Then they add the second element. And so they again check if I now make my 6, like if I make it, if I split it now vertically, what does this mean for my aspect ratio? And in this case, it improves the aspect ratio of the previous one, so we have closer to 1 aspect ratio. Then they add the third element with the number 4 here, but then if they check the aspect ratios, they have actually made the aspect ratios worse, right? And so they backtrack and instead add 4 as its separate node here in the unused space. They add the 3 thing here, check aspect ratios have improved. Then they add 2 here. In this case, the aspect ratios of 4 and 3 gotten worse. And so they move to this own use space, and so on and so on. So this is kind of the idea of this algorithm. And by doing this, you get these nice squarified tree maps. So here's an example comparing the original layout algorithm with the one on the right. Anybody like, why do you find anybody find the left one here more appealing? A lot of shaking heads. So yeah, clearly that's an improvement, right? Of course, we still have the problem of very small rectangles, but that might not be that much of a problem if what you care about is really the big chunks here. And so like I talked about, like this is kind of like they actually published a tool which is still available for Windows to essentially visualize the content of your hard drive. So if you have a small hard drive and you want to find out where am I losing my space, you can actually use their tool. It's called Sequoia View. So these are screenshots from this tool. At least this one here is, I'm not sure whether this is actually available in the tool. The problem that I mentioned earlier, by like you kind of lose the structure completely, you kind of can get back the structure if you add frames. Like, do I have a better picture here? No. Well, so you can, for each level, you could dedicate a little bit of space so that you can understand the structure. So you kind of like represent this, but then in this case, you kind of like, if you're looking, for example, for your biggest file, you don't really care so much about the hierarchical structure, right? You care much more about like where are the big elements. So depending on whether you care for the backbone or not, this is the approach that you could take or not. But even then, here, if you like even like reading the tree topology from this chart is still pretty difficult. And so there are tools now that we can use in our hard drives for both Mac and Windows, also for Linux. Retrospective for Mac, Sequoia View by this research group on Windows, and I have actually run this here on my computer. This shows you kind of like my work folder with all of the different things, and you see I have like a lot of tiny files in here. These are actually photos. And if we look somewhere here, this is like, you can't probably see this stuff here, but here I borrowed a GoPro from a friend, and now my photo directory is full of those like insanely large GoPro videos. And if we go down here, we see that here, well, this is not a GoPro video. Here, this is my work stuff. And so you can see that if you hover over this, like here's a graph database, this red highlighted piece here that we're storing. And then this is probably the lectures. And this is actually like my Viz slides, and you can see that those slides are pretty big. You can click on any of those, and you can actually somehow also zoom into the directory you use. So this is kind of like a useful way to like look at your file directory. This is like the infamous stuff that I used way before I knew what infamous actually was. Okay, so the alternative to, like one alternative to these tree maps, if you want to use an implicit layout, is a Sunburst. And so this is also quite simple. You start with the root node. The root node is represented as the innermost circle here. And then you add these segments of the circle like for each level. So this would be one large subtree of the root. Here we have another one. Here's a small subtree, and so on. And so what you can see here is quickly that, like, I again can easily visualize the size of the contained files. Each of these directories, like if you think of this again as directories, it could be anything. But each of these directories is as big as the sum of its leaves. But what you can very clearly see here is the structure of the tree, right? So it's kind of easy to keep track of the tree. This is actually a technique that originally was developed by John Stasko, and here's like an implementation that a student of mine did a while ago that has some fancy focus and context method. So you have this focus sunburst in the center. You can click on any segment, on any sub-hierarchy, it will pop out this sub-hierarchy and represent it as an outer layer. It also has smart labeling with it labels the biggest elements at each level, coloring to emphasize the tree structure and so on. Very related to the Sunburst is the Icicle Plot. And the Icicle Plot is just like if you take the Sunburst and unwrap it linearly. So you kind of like have, as I showed earlier, this Van Gogh-Tilford layout for node link diagrams. We have this circular and this linear layout. This is just a linear version of the Sunburst, right? And so it's maybe like a little bit less visually attractive, but of course much easier to implement. And yeah, it works the same way. This is again the flare hierarchy. This is a D3 implementation. You have the root, and then you have all of the different levels, and then finally you have some leaves at the bottom. And so if we compare those three, like which ones would you prefer and why?
What?
For what? Yeah, like depends on the task. You can come up with a task. Yep.
I've used that hard drive tool before, and it's super helpful. So I like to leave for this one for files where I'm like, okay, I have to I should probably delete Assassin's Creed because I have to forget. I use it.
Yeah. So tree maps. One vote for tree maps. Any other
Tree map.
tree maps? People like tree maps.
I like the top one quite a bit. Even though there's white space in there, it's nice to see it in a flat context rather than regular.
Yeah.
Can we turn it on its side and call it the Mac file explosion?
Yeah, you can try to do that.
Yeah, I have seen something like Radial Plot in like performance analysis tools that show sort of like time spent in functions. And
Yeah.
it's very nice there.
I think the Radial one is prettier, but I have an easier time understanding and looking at the one that's just linear. That has something to do with the curves and angles not registering as well as straight lines.
Yeah.
I also like the Sunburst one, that if you could get something that shows where you're at in the overall structure, so as you're zooming in or zooming out, I quickly lose context of where I'm at. So if I knew where I was, then I can quickly go back there.
Yeah, that's a good point. You can, like, if you would build a system like this, you definitely would want to add a feature like that that keeps you situated if you drill down. I guess my personal opinion is I do like the Sunburst a lot because it shows me the tree structure. But also, like, one thing that I dislike about the Icicle Plots is that they give so much space to the root, right? So, like here, the root is comparatively small, but here it's kind of like a fifth of the whole screen space. And somehow this kind of feels a little bit like, yeah, sure, it looks better. It feels a little bit, I don't know, more useful use of the space to me. Of course, if I just care about the leaf set, like really just finding the biggest files on my computer, then tree map is hard to beat. Okay, so if we kind of reflect a little bit on implicit representation, they are very space efficient because we have this lack of explicitly drawn edges. We don't have any overlaps, so they scale up very well to large graphs. If we think about the tasks, attribute-based or topology-based tasks, they're well suited for attribute-based tasks on the node set or the leaf set, depending on which technique you use. And depending on the spatial encodings you could also use them for topology-based tasks, like traversing, like from one leaf, finding the shortest path from one leaf to the next leaf is easy with Sunburst and Icicle Plots, but almost impossible with the tree map, right? And of course, the cons is you can only represent trees because like, you can't find a spatial arrangement for a general graph that works just like this. And of course, the node positions are used to represent the edges, so you cannot freely arrange them. So this doesn't work if you want to show something on a map, obviously. And they are useless to pursue any tasks on the edges. So if your edges have weights or like even direction, these are not the right visualization techniques to use there. So there's this website, this tree visualization reference that claims to collect every tree visualization technique ever published. They're not curating them for quality, it's really just a catalog. And you can go there. It will take a while to load because there's a lot of images. And they have kind of like, you can pick, okay, I want 3D representations that use implicit layouts, and then you get something like a 3D Sunburst sphere here. Or like strata tree map. Yeah, this is like, there's a lot of stuff out there. Or some kind of spiral step tree. Of course, I picked like a bizarre combination right now. If I switch back to 2D implicit layouts, you get all of this one. Yeah, you get all of these implicit layouts here. So you can see there's plenty of implicit layouts. Or if I want to look at hybrids, if I want to, like the other thing that like we have kind of like radial versus axis parallel. So if you have the radial layout in 2D and implicit, then we'll have Sunburst here in its early examples. So here's like a couple of early versions of Sunburst. Okay, I think Carolina mentioned much of this, but if you want to visualize a network and don't want to code, you can use Gephi or Cytoscape. I personally prefer Cytoscape. Cytoscape is like super well maintained, and there's like a tons of plugins in there. It's kind of targeted towards biologists, but you can really use it for any kind of data set. And then there's the Cytoscape web library that Ilkin has talked a little bit about, that you can use to draw trees on the web programmatically. So that's useful, but you don't really have a ton of power to actually customize it all that much. And then Network X is like a Python way of drawing networks quickly. Okay, so any questions about networks, graphs, or trees before I move on to the second part of the lecture? Great, so if not, I'll talk a little bit about tasks, design, and evaluation. And I have to say that like, I think I would like to spend like at least a full lecture on each of those, but there is only so much we can do, so I'll give pointers on how to learn more about each of those topics as we talk about them. And so, like, why do we care about task analysis? First, like, when you saw me if I critique a visualization, I always say, well, it depends, right? This is the usual answer for everything. Like, it depends on the task and on the data set. And we can think about tasks a little bit more structured. So first, there's kind of like two approaches to creating visualization techniques. And I think that like we have the problem-driven and the technique-driven approach, and essentially that in industry or in real life, if you want to say it like this, most people try to do something problem-driven, right? They find a problem and try to solve it. Visualization researchers sometimes, and maybe some people that like want to sell a product to like the masses, they tend to be technique driven. So you have an idea for doing something, and then you kind of like try to find problems that match it. But these kind of like differ a lot for like what are the tasks and how do you address like your task analysis. And so we'll mostly be talking about problem-driven approaches to task analysis today. So we have this top-down approach, we identify a problem encountered by users, we design a solution to help users work more efficiently, and in academia we sometimes call this a design study. And so I want to talk a little bit about this paper, A Nested Model for Visualization, Design, and Validation by Tamara Mansner, who was the author of our textbook. And just as a note, this was going to be also like one of those papers that will be on the test for the grad students in the room. So like, what is this paper about? Has anybody read it?
Yeah.
Want to give a brief summary?
She came up with like a 4-step process. So you start with defining the problem, abstracting the design, choosing the encodings, and picking the efficient algorithm.
Exactly. So we have these 4 steps, and why does she like separate these into those 4 steps?
Because if you skip if the one before you is bad, then everything below it is bad.
Exactly. So this is kind of like a hierarchical process, right? You start, like if you get it wrong on the outer layer, you will like maybe design something that doesn't completely address, or that doesn't address the problem that you're actually trying to do. What else does she talk about here? Like she talks about those 4 steps, but how does she talk about how can we avoid making these mistakes? Okay, maybe I'll just show a couple of figures and we can talk a bit about it a little bit more in detail. So, like, what's the purpose of this model? And by the way, it's just like at the VIS, this was published in 2009, and the VIS conference has this test of time awards, and this was given like a 10-year test of time award as one of the most important papers. Or every design decisions, like what are the justifications along every step of your design, and to analyze aspects of the design process broken apart into these 4 different concerns. And these concerns are like very different, as you'll see. And the other thing that it really emphasizes is that you can validate your design at each of those steps. And you can validate either immediately before you build something or afterwards after you have built something. And you will get kind of different quality evidence for each of those steps. And so the goal is, of course, to like be a better visualization designer, so that you want to avoid making ineffective solutions. So this is the 4-step model that we talked about. On the outer level, we have domain problem characterization. So this is really when we try, like this is again all for like applied work where I try to find a solution to a real world problem. So what I do here is I sit down with somebody who has an analysis problem in the real world, and then I really try to understand what is their domain problem in their own language. Then in the next level, I do this data and operation abstraction design. Like I try to kind of like understand the domain data set, the domain problem, and to translate it into terms that we as computer scientists understand, right? So for example, if somebody says, I want to kind of like analyze differentially expressed genes, you would break this down into, I have tabular data with gene expression, and I want to compare 2 different sets of them. That would be kind of this translation steps. Then after you've had this data operation abstraction design step, you can actually, as somebody who has gone through this class, you know, okay, Alex told me if I have tabular data, these are my 17 options to visualize tabular data. And now you can pick your appropriate encoding or interaction technique. And then finally, you have to like write the code and the algorithm that creates your visualization technique. And depending on what you do, this is a 4-step layout. This can be like some pretty sophisticated algorithm that can potentially be slow. And so, so this is the basic idea of how to actually approach the design. And I recommend that if you have a builder visualization, that you actually think along these steps, because it kind of helps you be explicit about what you're doing. Here's like this idea of like what can you get wrong at each of those stages, and what can you do about it. So like what you can get wrong at the domain problem characterization step is to pick the wrong problem, right? This isn't the problem that you need visualization for, right? So in that case, you've made a mistake, and you should just like say, hey, here's like my machine learning colleague, maybe talk to them, and they'll figure out your problem. So how do you validate this? Like you have to observe and interview target users. Like this is like, as you'll see, there is always this validation before and validation afterwards. And the validation before the implementation are usually a little bit vague, right? But this is just the nature of things. A threat at the second level is that the data operation abstraction design is that you simply get it wrong. And how do you validate that? That's kind of like, doesn't actually specify here, but yeah, just don't get it wrong. Just think about what you're doing. At the encoding interaction technique design, you could choose an ineffective encoding or an ineffective interaction technique. What you do here is really like just to write out the arguments. Like, do you know exactly about like, which visualization technique is suitable for that and for what, and you know why? And if you like are concerned about an inefficient encoding, then you kind of like by explicitly justifying all of your steps, you can kind of counter that threat. And then finally, at the lowest level, you could have a slow algorithm, or like it could be hard or impossible to implement. You can validate by analyzing computational complexity. We know that the computational complexity of a force-directed layout is n to the power 3, and so we kind of like can get a sense of is this going to work for our data. Then we implement something, and then after we've implemented it, we can do like a more rigorous evaluation at each of these stages, right? So here we can measure, well, more rigorous is, at least for the inner step, isn't probably correct, but here we can actually validate it by measuring the performance, either in time or in memory. Here we could do like a quantitative or qualitative evaluation using not expert users, but anybody, like people in your lab, for example. You could run a lab study. You could measure human time error for operation. At the data operation abstraction step, you could test on target users. So is it actually useful for the people that are designed it for? Do we have these anecdotal evidence of utility? You could run a field study. You could document human usage that are your collaborators that you built the system for, are they actually using it? For example, are they using it to create paper figures or to analyze their data? And then on the top level, was it the right problem? Was it useful what I did? You really can only observe adoption rates. Are people picking it up? Is it useful to somebody beyond just the narrow scope of what you designed?
Is this class only the middle, the greenish square?
No, I would say this class, like, we don't talk too much about this first thing here, but we do talk, well, in this lecture here, we really will focus mostly on domain problem characterization and data operation abstraction design. But yeah, this is like a little bit, in this class we have, especially if I talk about visualization techniques, I talk mostly about the green square and a little bit about algorithm design, but not all that much. So basically, this is kind of the process simplified. What you need to do is you need to understand the domain problem and really understand it, then map it to an abstract task and to an abstract data set. Then you have to kind of consider data type and some other factors that often play a role, and then you can identify and implement a suitable visualization. So that's kind of the 4 bullet point gist of this design process. What does domain characterization actually entail? It's about the details of an application domain. It's a group of users in a target domain. It's about their questions and their data. What it exactly look like varies, of course, widely by domain, right? We've done projects with poets and we've done projects with neuroscientists, and those are very different domains, and they they are very different in how you, like what the data is and how you interact with those people. But one thing is really important is that, like, once you do your domain characterization, you must arrive at something that's specific enough to continue with. You should, you should have data available, and you should have at least a good path to getting data. And the other thing that you need to realize is you cannot just ask people what they want. Right? There's this quote attributed to Henry Ford. Like, it's probably not actually him, but if I asked people what they wanted when he was designing the car, they would have said faster horses, right? And the point here is that people don't know exactly A, what they do, and B, what they want. They kind of like have a perfectly good understanding of their domain problem, but they're not the visualization experts, right? You're the visualization experts, so like, don't let yourself be guided, but I need to have this like that, or this is exactly what I do. If you really want to be sure, you have to observe people and study what they actually do in some way. So the idea is that introspection here is hard. If you characterize a domain problem, we have kind of like this infinite number of domain tasks, right? Every like user will have like, I need to kind of like find the largest file on my hard drive, or I need to find the drug that works for this kind of patient. These are completely different domain tasks. But you can break them down into simpler abstract tasks. And if you do that, we actually know how to address these abstract tasks. Like finding the largest file is basically a locate task in like a, for example, tabular or hierarchical data structure. So we know how to do that. So if we can identify this abstract task and data combination, the solution probably exists, right? So you can kind of like, you basically just, this is the hardest step, like translating from this domain problem to this abstract data, to this abstract task and data space, and then you can identify like what is actually out there that works for that. So, for example, if I have an abstract or like a domain-specific task, like me as somebody who likes to watch movies, I could say I want to find good movies. So what does it mean, right? Like, what's a good movie? This is tricky, right? There's many different things of how I can think about a movie, so I have to think a little bit about how can I like abstract my data in such a way. But domain-specific, there isn't really like, this is the domain here is the general population. Everybody's interested in movies, or maybe even movie enthusiasts. So this is kind of a simple example here. If I like, and then like I'm gonna keep using this example of finding good movies at each of these steps. And so data and task abstraction, this is what I talked about earlier. This is really the what, why, and mapping it into generalized terms. You want to identify the task that the user wishes to perform, or they already do that. You need to find the data types and a good model of the data. And very frequently, actually, you must transform the data for a better solution. So very frequently, you don't want to visualize the raw data, but do some transformation to the data so that you can actually tackle that problem. And of course, this depends on the specific task and on the environment. So in the good movie example, what is a good movie for me? Is it highly rated by critics? Is it highly rated by audiences? Is it successful at the box office? Is it similar to movies I liked? Is it specific genres, right? Do I like despise horror movies? Then that I should factor in. And so what would be data sources? I could try to get data from IMDb or from Rotten Tomatoes or from other critics, aggregators out there, or even directly from news sources like that. Or I could like use my own history of viewing of viewing movies to kind of feed into the similar to movies I like. Okay, and if we then want to build encodings and interactions, it's really about all of the stuff that we talk a lot about in this class. It's the design of the visualization techniques, the visual encodings and interactions, and of course ways to create and manipulate the visual representations. And all of these decisions here may be separate or intertwined between different aspects, and we kind of can use visualization design principles to drive the decisions here. So we kind of like on everything we know, like what is good practice, what are like appropriate visualization, what are good perceptual principles, we can apply that to create these encoding and interactions. And so to find good movies, example, I could say like, hey, what I think is a good movie is a combination of audience ratings and critics ratings, maybe a little bit with a bias towards critics ratings so that I care more about the opinion of critics. And then I want to filter them by genre, for example, to exclude horror movies. And like the visualization technique or the visualization idiom that can do that is this stacked bar chart for rating and some interactive filtering to remove the genre. And so that would be like a reasonable solution for this problem. So here's like a real life example. This is from a project that I did with Novartis, and I don't want to go into too much detail, but the goal here was to control data quality for gene splicing data. And so like we actually wrote up, like this is one of 4 goals, and we wrote up 4 domain goals here, like explore differences between samples and groups, discover novel isoforms, that's a very high level goal, evaluate isoforms, and control data quality. And then we broke this down in these abstract tasks here, judge the magnitude of a sample or group, compare samples and identify within group variants and outliers, and so on. And then basically what we did is we come up with a visualization technique that works for these particular tasks and therefore works for these high-level domain goals. Okay, so like I talked about tasks, and now there's a lot of task analysis and task taxonomies out there. For example, I mentioned attribute-based tasks and topology-based tasks when I talked about networks. But you can also kind of come up with these tasks for like general visualization, like on a very high level, what are the things that you want to do? Things like spotting outliers, spotting trends, and so on. And so there's this paper by also Tamara Mansner, and it's also kind of like detailed in her book in one of the early chapters about these kind of general purpose visualization tasks. It's Matt Bremer and Tamara Mansner. She kind of like splits it up into these 3 high-level categories: analyze, search, and query. Analyze is about high-level choices, consuming versus producing. Am I just reading a visualization or am I annotating? Searching is about finding a known or an unknown item and then understanding its properties. Querying is finding out about characteristics of an item by itself or relative to others. This sounds very abstract now. Let me give you a couple of examples. So the high-level actions on the analyze level here are this consume versus produce. And so like tasks can be either to discover something new. For example, I don't know something, and I don't know my data set, and I want to discover what's in the data set. Or it could be a presentation, right? Somebody else has curated for me and wants to present it to me. So we have this classic split: exploration versus communication, exploration versus explaining. And then you could also just like not even want to learn something or study something. You could simply just like use a visualization for your enjoyment in a casual or social setting. And then like when you think about producing, what do I mean by producing data? Well, when I work with a visualization, I often also want to annotate something or record what I did or derive new values. For example, take a tabular data and wrangle it so that it becomes a network. So this is also like a problem that you can tackle with visualization tools. On the mid-level, we get a little bit more specific. We want to either search or query. And for searching, they distinguish between like 2 dimensions. Is the target known or unknown? Is the location known or unknown? If the target is known and the location is known, it's just a lookup. If the target is unknown but the location is known, we browse at this location that we know. If the location is unknown but the target is known, then I have to locate the target. And if the target is unknown and the location is unknown, then I have to free explore, right? So I basically look at the data and try to find something interesting. And then for the query pieces, like the question that these tasks ask is, how much of the data matters. Is it only one data point? Is it some of the data points? Or is it all of the data? And so if it's only some of the data, you want to identify those data points. If it's some of the data, you want to compare them. If it's all of the data, you want to summarize them. So here's an example of comparing and also of deriving. So the left here is an example of comparing. I have like these different financial crises and how they affected the GDP in terms of like percentage change. And you can see that the 2008 financial crisis in the euro area versus in Britain versus in the United States, like this was the Great Recession in 29, and how Greece compares to that. And so you can see that while the euro area and Britain actually had like a comparatively mild recession, the recession in Greece was comparable to the Great Recession in the United States in 29. So here we do this comparison task. And if we interactively wanted to like derive the data set here, this would be the result. So here we have like a representation that doesn't show us the absolute values, but it shows us the change on a year earlier, which is kind of like a different representation for different tasks, for a different kind of question. On the lowest level, we think about what are the targets. So we have things like trends, outliers, and features. Do I want to identify these trends or outliers or features? Or in an attribute, like for attributes, do I want to look at one or many attributes? Like is it a distribution, or do I want to identify extremes? Do I want to identify dependencies or correlations or similarities? And then in other data types, we have specific tasks or specific targets. We talked about network data, where we have topology, like where we want to look at neighborhoods or a path. And in spatial data, we want to identify shapes. So here's an example of like spotting outliers. How did the job market develop since the recession overall? There's this New York Times visualization here, which, yeah. So like this is like how like each job, how the recovery was for different parts of the, like for different job descriptions. And so like, this is a storytelling example. But what is interesting here is to kind of like spot outliers. Like this is recovery since the Great Recession, or since the recession in 2008, and we can easily spot like outliers here. Electronic shopping and auctions has gone uphill between 2004 and 2013, so this wasn't really impacted by the recession. And if you keep going, they kind of highlight some of the trends. So here, like medical economy, like the medical industry just didn't really suffer by the 2008 recession. But of course, anything related to housing went really terribly bad, with the exception of real estate escrow, fiduciary, or other services. So this is probably people handling bankruptcies. And you can keep scrolling and so on, but essentially you see like we kind of want to here analyze trends or outliers or correlations or anything like that. So now I want to kind of like do a task abstraction exercise. And so this is kind of like, this is hard to do in class, right? But I'm just still going to try, and I'm going to give you an artificial scenario. That you've been approached by a geneticist to help with a visualization problem. She has gene expression data, which measures the activity of genes for 30 cancer tissue samples. She's applying an experimental drug to see whether the cancer tissue dies, as she hopes, with this drug. But she finds that only some samples show the desired effect. She believes that the difference between the samples is caused by differential expression, so different activity of genes in one particular pathway, which is kind of like a network that describes the relationships between genes. She would like to understand which genes are likely to cause the difference and what role they play in that pathway. What I want you to do, again in groups, is to do this task abstraction and encoding design. And I'll give you guys 12 minutes for that, and then we have like 3 minutes to go over like one possible solution that I have. I can go say. Yeah.
In the cell with the yeah, and then these like so I don't know how hard it's about I think in general, people are Yeah.
Yeah, gene expression, plot sample.
That's like what I meant with the comparison of like responses to others, non-responses.
Yeah, because this one has
I said, yeah.
Okay, so did you find this hard to do?
Yeah.
No, yeah, it's super hard, right? Because you get one paragraph. In reality, you would probably have like a couple of hours of meetings to understand this problem and get data sets. Anybody want to share how they approach this? Yeah.
Well, there's a decent amount of like rereading just to like make sure I understood what they were talking about. As part of doing that, I like to like kind of write out stuff. So since I'm familiar with sort of data structures and things of that nature, as a programmer, one thing I did is I like kind of organized their data set in a way that just sort of makes sense to me. That helped me as I was going through the rest of the discussion because I could refer back to that.
Yeah. Yeah. So probably most of you, like in the 10 minutes I gave you, didn't get much further than like trying to abstract the data, I assume, and nobody really did a visualization design. But I kind of like, you can try this at home. I just want to kind of give you a little bit of a sense of how what I talked about earlier, which probably sounded like a lot of words and maybe not very concrete, how this applies in this case here. This is a project that I've actually done. Like if you think about this, we say like the task abstraction is we have, like she said, only some samples show the desired effect. So what we have here is actually two groups, right? So we can actually do like a data derivation step and say we have those that respond and those that don't respond, and create a new categorical attribute to separate those two samples, right? So then we have in the text here the difference between the samples is caused by differential expression, different activity of genes in a particular pathway. If you would like to understand which genes are likely to cause the difference. So again, here we have like a long list of genes where we measure activity. And then now we can compare like between the one group and the other group that we just created, what are the genes that are very different in those two groups, right? We can write a little algorithm that does it for us. It looks for full change between those two groups. So, and then we have a list of maybe like 50 genes left or something like that. So we identify those genes, and then we compare the gene expression of pathway genes between the two groups. And so we go in and like retrieve this list of pathways from like an online data source, and each of these pathways has a list of genes, and we do something let's call like a gene overrepresentation analysis. So we look at which of the genes that I have in my subset here overlaps with any of those groups, and that way we can identify the pathway that we care about. And we can then identify the outliers, like which of the pathways is extremely overrepresented. So that, yeah, it's kind of like mostly algorithms and deriving new data, but this is kind of like how you do this data and task abstraction. So then the next step is you would like to understand which genes are likely to cause a difference and what role they play in that pathway. And so if you look at the second clause here, is what we want to do is locate the outlier in the network, but also explore the topology of the network. So where does like an outlier gene, where is that in the whole network? What role does it play in that network? And then if we go into encoding design, like what we end up with is a tabular data set of about 30 samples and 30 genes. So that's not too big. We also want to compare groups and spotlight outliers. And so here's a couple of visualization techniques. Like I could use dimensionality reduction, scatter plot matrices, parallel coordinates, heat maps, and bar charts. So that's kind of like my simplified design space for visualizing the 30 by 30 matrix. And so if I look at dimensionality reduction, well, it doesn't really show the raw data, and it's not great for comparing groups, so maybe I'll dismiss this. Scatter plots, 30 dimensions is a little bit too much. This is a scalability issue, so I'll dismiss this. Parallel coordinates would work with 30 dimensions, but I need to do some color coding for comparison, so potentially a solution, but maybe not the best one. So heat maps and bar charts are going to work fine for this particular example here. We have a spatial separation of the group. We can look at this differential expression easily, and bar charts work easily too, because 30 by 30 is pretty feasible, and we have the encoding advantage over the heat map. So in this case, like bar charts, like a table of bar charts might be the best approach. And so this is kind of like what we did here. So we came up with this like list of like with this bar charts here in this particular example. The second piece is for our network. We have about 30 genes. We need to explore the topology and look up a node. So do we want to use an adjacency matrix? Well, it's a little bit tricky to see path. This is kind of something that you care about in the pathway, so it doesn't really work that well for the topology-based tasks that we care about. Tree map, no, it doesn't really, like, it's not a tree, it's a network, so we can't use a tree map. So node link diagram works well because it's fairly small, and we can then combine the table with this node link diagram and highlight whatever like we look at in the node link diagram and in the table to kind of integrate between the two of them. So that would be kind of like an example of how you could approach this. And so here, like this is the choice that we made. We took this node link diagram representation and then highlighted it here and then linked it up to the table that I showed before. So this is just an example. And next time I'll talk more about how we actually design visualizations. Like what is the not what is the design space look, but what is the process. And so we'll continue with that, and then we'll talk about maps after that. Well, yes, but I will not.